Okay, so our last, hold on, I'm getting a little bit of an echo. All right. So our last lecture on input modeling hopefully complements the lab that you've been working on a little bit here. So a couple of announcements first. So yeah, lab 8, the input modeling lab, data collection. I've given you some data. I've added some reminders to the spreadsheet about how to input things into the input analyzer. So when you grab a column for part 1, make sure that you grab just the numbers, not the header. So it really has to be just a single column of numerical data, export out as a text file just of numbers. If you leave the header in the text file, the input analyzer is going to give you an error message like, this isn't a text file or something like that. It's not going to make any sense, but that error means usually there's a header that's been left in there. So make sure that when you're doing part 1 of the lab, that as you export those columns into text files to open up in the input analyzer, you only export the numbers, not that header across there. And I've tried to add a reminder to the slides as well as to the data sheet. I did that a day or two ago. And so if you download those fresh, you should see those reminders in there. This is meant to be useful prep for your final project and your input modeling report. Next week, there's no formal lab assigned, so you can use that time to work with your team on gathering or processing data for your input modeling report. I'm not expecting you to gather all the data for all your input models. Your input modeling report is really just supposed to show me that you have a system in mind, you have variables in mind that you think that are involved and important in the system function, and you have the ability or access to the system to be able to go out and grab data on some of those variables. And so again, like you might say that we think that we're going to need these 5 input models, but you maybe only have to show me one of those so that I can see that you really do have access to that system and that you've got some momentum that you could build these input models if you absolutely needed to. So it's not supposed to be a really burdensome assignment. It's just supposed to allow me to evaluate what project you're doing and see that you've got some momentum going on it. And then I will then read all of those and give you some feedback back about, well, maybe this is a little too ambitious. You could dial this back. Maybe we need a little bit more, and so on and so forth. And after that, we've got labs 9 and 10, which are on more advanced arena topics. And then the rest of the labs for the semester are just meant to be time for you to work on your final project. So I've talked about the final project here, the names of team members. A lot of those have been coming in. Appreciate that. When you submit them earlier, it's a little easier for me to process them, so I don't have to do them all at once. But definitely, if you haven't submitted those, or if a team member submitted those, remember every team member has to submit those. So it's not just one team member, it's every member of the team. So make sure you get those in. And then about a week later is that input modeling report you're talking about. The ICAs are available. This new homework is released. It's 2 questions and a little bit of bonus. This first question is basically doing a chi-square analysis on some Poisson distributions and some data. And the second question is doing a power analysis. So those are things that I've linked to examples in the book. I've got to give you some extra resources online. And of course, we'll talk about these things in class. I think you get about 2 weeks to do that homework. And then after that is our last homework, which is an arena-based homework. All right, any questions on the timeline moving forward? I see a lack of skateboards and scooters, and I feel bad about that for some reason. I appreciate you guys working with the building rules. I know it's really inconvenient, but you know, it's who knows how they'll respond. And so I don't want you guys to get fined or things or whatever. But so I'm not trying to be the bad guy, but I do appreciate that. Okay, so moving on to the input modeling. This is you start with a general process like this in Arena. I've got in a queuing system like this, you've got arrival processes, you've got service times, and so you need to fill in those. So in the kind of simplest case of a queuing node, the so-called MM1 queue in Kendall's notation, then In an MM1, you've got this. I mean, if you haven't seen this before, you probably will in 470. This is just an encoding of the input models, like all of the sort of important information that you need to know for this node. And this basically is a queuing node, this single server queue here. So it's not much of a network, it's just kind of a single node. And when we look at MM1, the M means Markovian or memory list. That just basically means exponential. So what MM1 means is you get one server. The service times, that's the middle M, are exponentially distributed, and the interarrival times are also exponentially distributed. So it's just encoded as that. Now, there are other queuing nodes that look exactly the same up here, but we write them down. We say, actually, this is an MD1 queue. And that will mean that the interarrival process is still exponential, but the service has this code D for degenerate or deterministic, which just means it's a fixed service time. So every customer takes exactly the same amount of time to get through there. There's DM queues as well, where the degenerate deterministic is the interarrival time, but then exponential service times. So there's a bunch of different ways you can throw these in, and there's a bunch of different codes that represent the different distributions that would go into each one of these. I'm just trying to drill it down how important this input modeling is. It's the exact same model up here, but very different distributions going into the interarrival process as well as the service process. So something like, and I'm not expecting you to memorize Kendall's notation. Again, that's more of a 470 type concept, but just kind of show you that the fact that Kendall's notation exists, that we have these compact things, shows how important it is to get the input models right and to specify them. So they've got even things like an MX EK1Q. Well, that MX means that it's exponential arrivals of batches. And those batches have sizes that are distributed like the random variable X. So that looks a little bit more like some of the, like the kind of the muffin sim and those sorts of things, where we had batches arriving. Whereas the middle, the service time EK, that's an Erlong K. So in that case, they're saying here that the service time is actually the sum of exponentials of K exponentials, which actually makes a lot of sense. If in order to wait for something to be served, you have to do a bunch of things that themselves individually are kind of like a failure time distribution. They take a non-negative amount of time that's independent of all the other amounts of time, but you have to do like 5 of them together. So you add them together and it looks like an Erlong K, which if K is big enough, will actually look kind of hump-shaped, and so it'll look almost normally distributed. And so, so it's not uncommon to see Erlong as a service time distribution. And if you were to go to Wikipedia on Kendall's notation, you would find a whole table of these codes that all are specifying shorthand for the input models that go into either the interarrival process or the service process. And so again, that just shows how important it is to get those things right. Otherwise, we wouldn't actually have to specify them. So as you start working with queuing systems and things like that in your jobs as operations researchers, then you're going to see these things and you're going to be asked like, well, how do the parts arrive? How do the customers arrive? How are they distributed? And it's not just that you got the logic right, it's that you've got these distributions right. So that becomes really important. Okay. I'm stuck for some reason, so you tab back and see. All right, there we go. So yes, how to choose. So that's kind of what this whole unit is how to choose that. So we talked about how to collect the data. We talked about how to generally figure out what the family is. Today, we're going to talk about choosing the parameters for the distribution and assigning and evaluating goodness of fit. So any questions about what we've gone through so far? Everybody feel pretty much on board? Questions online? Okay. All right, so this is going to require a little bit of stats review. So can somebody tell me your definition for what's the meaning of level of significance, or alpha? Maybe have like a back of the envelope definition for what alpha is. Online too, I'm happy to see if anybody said anything. So fundamental concept, hopefully review from 380 and maybe some other classes. Anybody? Nobody? Yeah. Well, so that was so the answer there had to do with that was a very specific answer about if you have a certain distribution or whatever. But can we get more sort of generic, like even before we get the distribution, like I mean, what is this? You know, like if I just want to phrase it in the general terms of hypothesis testing, then how does alpha fit in? Yeah. Wrongly rejecting a null. So that's a good sort of like definition. Like that's a totally correct. But can you unpack that a little bit? So um, what would that, if you were to sort of explain that in a few more words, how would you sort of say, what do we mean by wrongly rejecting? And that's okay, great. So the answer there was if the null hypothesis is true, then what's the probability, what's the maximum probability that you're going to wrongly reject it and say it's false? And so it's like if you hear a noise, that noise could be the null hypothesis is just a creak that the building makes. Whereas, you know, an alternative hypothesis is that it's something that is out of the ordinary. Maybe a water heater has broken and a flood has started to happen, and that's a significant thing that we need to detect because we need to go and fix that problem. But it could just be the normal creaks and cracks that a normal building makes, since that would be our null hypothesis. And so we can come up with a strategy for when do we respond to these noises, and we can ask how often are we going to, given a null hypothesis is true, i.e. it's just a creak and crack of the building, how often are we going to freak out and run down the hall and find out the water heater's totally fine? So that's kind of what this level of significance is here. So when we're designing these tests, we can kind of set, we can sort of like when we say like, how do we set alpha equal to 0? We like, even without saying what test I'm going to use, a t-test, a chi-square test, or whatever, I can design a test easy that has alpha equals 0 for pretty much any hypothesis we're testing. So what does it mean for a hypothesis test to always have alpha equal to 0? Well, it's well, so the alpha part of that I think was right on. You have to remember the alpha here only applies to the if the hypothesis is true part. So what alpha equals 0 means is if the null hypothesis is true, if it is just a creak in the building, I will never ever conclude that it is something more than a creak in a building. It is a water heater breaking. So a way that I get alpha equals 0 in a hypothesis test is I just never detect anything. This is like just being totally chill. This is like, I am not going to respond to anything. Everything to me is the null. And that's how you set alpha equal to 0. On the flip side to that, how would you set alpha equal to 1? Well, that would be whenever the null hypothesis is true, 100% of the time, I'm going to conclude it's a deviation from the null. So if I hear any noise, I will always conclude that the water heater is flooding. In fact, even when I don't hear any noise, I conclude the water heater is flooding. So 100% of the time, I have that error. And so it's really easy to build hypothesis tests with alpha equals 0 and alpha equal 1. Here you never reject. Here you always reject. In other words, here you never react. Here you always react. And a real, useful alpha is going to be somewhere in between, where some of the times you react and some of the times you don't. And hopefully you don't commit too much of that error. So 0 is impossible because then your test, like you'll never actually go and fix the water heater. But, so then we just say, well, okay, what about 0.05? And that becomes hard. Like, how do we actually design this response policy so that I respond to some sounds and say that they're the water heater and other sounds they aren't, so that only 5% of the time I go running down the hall when I actually shouldn't. So that's how at least I define this level of significance. So with that in mind, how do we need to figure out how to translate that to chi-squared value? So it should be the point where if I ask you to lower your alpha, you'll know whether you need to raise or lower a chi-squared critical value. So if we think about how we've talked about chi-squared tests so far, then can somebody make a guess at if I make alpha very, very small, like close to 0, remember, if it's close to 0, we never detect a deviation from the null. What do you think happens to the critical values for the chi-squared test? Do the critical values go? And I saw it online, by the way, alpha is equal to type 1 error. That's true. And then they said, does that mean false negative? And we'll get into this like false negative, false positive stuff in about 2 lectures. And so I want to hold off on saying false positive and false negative, because we need to be clear what we mean by positive. And to me, a rejection is positive. So, but we'll get to that here shortly. So, but yeah, so remember, if I make alpha very small, then I never reject. I am just some super chill. So what does the chi-squared critical value need to be if I'm making alpha really, really small? Remember, chi-squared measures a deviation from the normal. The larger the chi-squared, the larger the deviation from the null. So if chi-squared gets small, what happens to, if alpha gets small, what happens to the chi-squared critical value? Does it get large or does it get small too? Any thoughts? It's a guess. You got a 50-50 chance. If chi-squared gets small, or as alpha gets small, does chi-squared get big? Or does the critical value for chi-squared get big? Or does the critical value for chi-squared also get small? It gets big. Why would you say big? Yeah, I'm not going to use the word confidence interval just yet. We're going to, but you're going. That's the right idea. That basically, as chi-squared gets small, we become extremely accepting. So I keep saying chi-squared. As alpha gets small, we become extremely accepting. And so what that means is we will tolerate major deviations. So it's kind of like if alpha is equal to 0, remember, that's when you're really chill. It's like nothing bothers you. Well, chi-squared, the statistic, when you calculate a chi-squared, that is the difference from the null. The null is like the uniform. You know, and you want to say, is this a uniform distribution? Well, the null is the uniform, and you look at the data, and if you look at the data and it's not looking very uniform, then you're going to have a high chi-squared. But if you set your alpha down equal to 0, then that critical chi-squared value that you're triggered to say this is not uniform is going to be really, really high. So alpha equal to 0 corresponds to a chi-squared equal to infinity, a chi-squared critical value equal to infinity, because you will never reach that threshold level, and so you'll never reject a null. And that's going to be the case for many, many, many of our hypothesis tests, is there'll be an inverse relationship between the critical value and the alpha, because most of our hypothesis tests are distances from a null. They might be distances in 2 directions. There might be distances in 1 direction, so always positive or positive and negative. But as those statistics like chi-squared go close to 0, then that means we're more aligned with the null hypothesis. And as they get farther away, we're less aligned. So if you make alpha small, the critical values will get large. So that's what I want you to start burning into your mind, this conceptual relationship between critical values and type 1 error. All right, so are there any questions about that? And so it's the inverse here, is if alpha gets large, so if 100% of the time you reject a null when you shouldn't, well, that just corresponds to having a chi-squared critical value of like 0. So any chi-squared is going to cause you to reject. So they're inversely related. So does that make sense? Any questions about that? Stats are not magical. They are very intuitive. You just got to learn the language. Okay. So then likewise, we could talk about p-values. And so when we talk about the meaning of a p-value, I've already kind of hinted at this, is, given that a null hypothesis is true, in a world where the null hypothesis is true, then what is the probability that we would get data that we observed that's this far away from the null or farther? So if the null hypothesis has got a distribution of outcomes and we get an outcome, then a p-value is what's the probability that we would get this outcome or even more extreme outcomes, where extreme is defined as like away from the mean of the null. So that's how we generally define p-value, but I need you to start thinking more deeply about p-values, because as you start using them more in arena, then we're going to see that having a low p-value or a high p-value maybe doesn't mean what you think. And so there are a bunch of scenarios where you'll get low p-values, and yet you really shouldn't worry about the null being rejected. And there are a bunch of scenarios where you'll get very high p-values, and yet you should not use that as evidence that the null is a good hypothesis. And I'll give you kind of some examples of that. So after flipping a coin, just a single coin, a quarter or something like that, twice, it comes up heads twice in a row. Heads, heads. That's it. So I do a binomial test to evaluate two alternative hypotheses. One, that it's a fair coin. There's an equal probability of heads or tails. And one, that it's a biased coin. Now, if I think about the outcome of two heads, in the fair coin hypothesis, I get a p-value of 0.5. So there's a 50% chance that this outcome, heads, heads, or something more extreme, and there's nothing more extreme in this simple case, could occur. Now, in the biased coin example, where they both come up heads, under this hypothesis, the p-value is 1. So if I want to rank things by p-values alone, then I maybe should conclude that two heads in a row means that I should assume that the coin is biased and always comes up heads. But does that make sense? Is that a good interpretation? Does anyone think that that's a good way to go with this? That if I see two heads in a row, I have to assume that's an unfair coin? Too small of a sample size. That's kind of what I'm looking at here. Like, we know from our personal experience that flipping a coin, you will very often get the same outcome twice in a row. So that's one way you get large p-values, is by having low sample sizes. So don't ever trust a large p-value. Now, the flip side of that I'm going to show you in a second here is you also need to be careful of trusting small p-values, because if I get more and more and more samples, I will necessarily make my p-value smaller and smaller. So here's an example here. After flipping the coin 200 times, it comes up heads 90 times. So now I test fair coin here. And the fair coin hypothesis, when I've got 90 out of 200 coming up heads, this binomial test p-value tells me it's 17%. And so that is not less than my 5%. So I might make the conclusion that I'm not going to reject this hypothesis here. Great. So that means that I'm not accepting the fair coin hypothesis, but for these data, 90 out of 200 coming up heads, I don't have enough data that I can say that the coin is not fair. But here's the kind of crazy thing. Let's say I flip that coin 2,000 times and it comes up heads 900 times. Same fraction. Now, if I do that binomial test, the p-value is way less than 0.05. So now, if I would have done this experiment, I would have rejected fair coin. But in this experiment, I would maybe not have rejected fair coin. So how do I make sense of these results? And the sample size is the big key here. The real coin is probably not fair. It's probably not perfectly fair. It's just close to fair. A real coin may not be perfectly balanced, so that if you did the kind of, the dynamical system analysis of it, that you could show that it definitely has an equal probability of coming down on either side. It probably has a slightly higher probability to come down on heads than tails, or vice versa, just due to the way that, you know, the divots are shaped on the outside of the coin, or some, you know, some dog poop that got gunked onto it or something like that. It's probably not totally fair. If I want to detect deviations from fairness, the more samples I take, I will eventually detect that deviation. So that's the kind of crazy thing about hypothesis tests, is if we just base them off of this, this bright line value of 0.05, then if you start taking a lot of data, you're going to start rejecting every hypothesis, because all models are wrong, but some are useful. All models are wrong there is really the thing that applies there. No coin is fair. You will always detect a deviation from fairness. There, if I think about two models of my mood, there's one model of my mood where the orbit of Pluto affects my mood, and another model of my mood where the orbit of Pluto does not. Now, if you just, were to take a little bit of data, there would not be a way to tell the difference in those two different models. But eventually, once you took enough data, you would actually be able to show that the orbit of Pluto has some small effect on my mood. And it's kind of the same thing here. There might be a very small unfairness to this coin. And if I take enough data, I will eventually detect that. So when you see extremely small p-values, you need to look up and be a little skeptical if you also see really large sample sizes. And then your question should be, what is the magnitude of the effect? Because here, when I look at it, 900 out of 2,000, that's pretty darn fair to me. So if that's sufficiently fair to me, then maybe I don't trust this rejection, or I have to interpret this rejection very carefully. So what I'm trying to get at here is, when we come up with hypothesis tests, we not only need to come up with an alpha value, which will be like 0.05, we also need to come up with a minimum detectable kind of deviation from the null. So when we talk about fair, you need to say, well, what is fair? And you're going to have to say, well, fair means somewhere between 45% and 55% heads. And once you have that, then we can start saying things a little bit more interesting and useful. If all we're saying is it fair? Eventually, when you take enough data, you will eventually show it's not fair. All right, are there questions about that? Does that make sense what I'm saying there? That the world is never the null hypothesis. So with enough data, you will always reject every null. And that's why you should be skeptical if someone just shows you a super tiny p-value, especially when they start using like exponential notation, like the p-value is e to the minus 23. Like at that point, look to see if they've got millions of data points. And if they do, then you really need to think, what's the effect size that was being operated here? And did you just detect a really small effect that's actually insignificant? So there's a question here. Can you remind exactly what the p-value means conceptually? The p-value is, and I'll just said this before, doesn't make sense, feel free to ask to clarify, but if the null hypothesis is true, so if it is a fair coin, then what is the probability that the outcome we would get would occur under this null hypothesis just normally, or any outcomes more than that? So in this particular case, we might expect that the fair coin would have 1,000 heads and 1,000 tails. But we also know that a fair coin will sometimes have 900 heads and 1,100 tails. And so the question is, how often would a fair coin come up 900 heads, 2,000 tails, or worse, like 900 or less? And that's really what the p-value is here, is that what's the probability that I'm going to get 900 or less heads for my 2,000 tries? And that's this p-value down here. So if you assume the null is true, what's the probability that you would get this outcome or worse? And that's the p-value. Hopefully that makes sense. Great. All right, so So with that in mind, so this is my kind of general rules here. So be careful with p-values. And this is why in Insight Maker, we're going to see that when you do, I'm not Insight Maker, sorry, I teach another sim class, and that's a program we use there. In the input analyzer, then in the input analyzer, it will do a chi-squared test and a ks test. And one of them will have a p-value that rejects your null, and the other one will have a p-value that does not. And a lot of times, the big difference between these has to do with how sensitive the tests are. And that's what we'll kind of talk about here. But because eventually, if you had enough data, all hypothesis tests will reject your hypothesis. So large p-values are only meaningful if there's enough data, and you always can generate low p-values by gathering more data. So if I had 1 million samples and a p-value of 0.8, then that null hypothesis is almost definitely true, because I've got so much opportunity to detect a deviation from the null and I haven't. So large p-values are really useful if you have a lot of data. Large p-values are not useful if you have very little data. Small p-values are best actually if you have less data. Once you have more data, then small p-values become kind of the norm. And this is why simple t-tests and other hypothesis tests are often not used in big data applications, because they've got so much data that any hypothesis you test, they'll be able to say, sorry, this is the real world. It does not match that simplistic hypothesis of yours. And so they have to come up with other ways to think about those data. So yeah, p-values, try to use them with small but not too small sample sizes. And then the more modern effect that we use in sort of other applications that you'll find in more advanced stats classes is what we call generalized linear modeling, where in this case, we actually try to infer effect sizes and not p-values. And so I look at a bunch of data, and if I look at the coins, I actually say, let me estimate what the fairness of this coin will be. And then that, it actually says, what is the effect size? How different is this coin from fair? That's much more useful in many cases than is this coin fair or not, which is really what a p-value is. All right, so any questions about that before I start making fun of the World Series? Questions online? All right, so when I started taking stats classes, it ruined sports for me, because it made me kind of realize that watching sports was no different than watching coin tosses. So as an example, best of 7 series in sports tournaments, you got 2 teams, A and B. What's the null hypothesis? Well, the null hypothesis is that they're equally matched teams. If you pair them up together, any given Sunday or whatever you want to put it and say it, then half of the time A will win, half the time B will win. And so we say the probability of A winning is 50%. That's our null. So we would like to set up a series of 7 games so that we can detect a deviation from the null. We want to detect if A is better than B or B is better than A. We'd like to be able to detect that. And the question is, are 7 games enough? Well, if we take Bernoulli trials here, wins and losses, so I got 6 wins and 1 loss in 7 games, and I do the binomial test there, then I find that I got a p-value of 12.5%, which is greater than 5%. So even with 6 wins and 1 loss, I can't reject the possibility that they're equally matched. And in order for me to really be decisive, I actually need one team to win all 7 games. To be statistically rigorously decisive, I need 7 wins. And then I'll finally get a p-value in the binomial test that's less than my critical value of 5%. But we know that the way these games, like, nobody would want to watch a 7-win series. That would be so boring. Why would you tune in and every single game, one team just gets beaten up by the other one? And so for marketing purposes, this never happens. And so they end up doing these best of type things that once you win 4, then it's over, because nobody's going to watch the other 3 games. So then we can start analyzing those outcomes. And so if there are 4 games and 4 wins, that seems like a boring series. The p-value for that is 12.5%. Still doesn't reach critical. All right, so 5 games and 4 wins. Now we're at 31%. We're in the wrong direction. 6 games and 4 wins, still going in the wrong direction. P-value is getting even bigger. And then finally, 7 games and 4 wins. You might consider this to be the most exciting series, but it's also the one closest to a coin flip. Because in that case, the p-value really is about 50%. So what we're saying here is that we think that we're deciding a winner, and that's the reason why we're meeting over these 7 games to watch this with friends or whatever. But in reality, we're just getting together to be socialized and fun. We're not actually trying to determine which team is better. Because in most of these cases, at the point where you have 2 of the top teams playing each other, it's not about who wins. It's about whether it comes up heads or tails when they flip this coin. So if we really cared about which team was better, then we would actually allow these series to go on for long enough time that we'd actually be able to sequentially sample long enough to reach significance. But that might mean playing a 30-game series. And nobody ever wants to watch 30 games of baseball among the same 2 teams. So this is one of the things where, like, in marketing, that would never happen. Likewise, if you think about it in voting, the same thing happens here. Like, the most important races are often the races where it comes down to one person getting 51% of the vote and the other person getting 49% of the vote. But if they're really equally matched people, then that one election won't be enough to determine whether you found the equally matched one. That could, an unfair coin will still come up tails a bunch of times. So if we really wanted to do voting right, then we would actually maybe vote over and over and over again, And so voting would sort of, you do some of the things that we already do a little bit. If you have, 5 people that are up for an election, you might get rid of all but the top 2 and then re-vote. And that's a little bit of this. And so if we really cared about finding the truth, we would totally reform how we did voting. But in reality, voting also, to some extent, is entertainment, because when things are equally matched, the designers of the voting system realized it's probably going to be just as good or bad with either one. So we're just going to do the easy thing and just take the majority. And statistically, it makes 0 sense, but it's just practical. So it's the same thing with sports. So this is why, when I started learning stats, it just let all the air out of the room for me in sports and voting and in so many things. And now I'm sharing that with you. So there you go. So any questions about this? This general idea that sample size is so important when we're trying to figure out if we can interpret p-values. All right. So if I want to formalize everything I just sort of said there, this is why we talk about things like type 1 and type 2 error. So we talked about type 1 error. So that's the maximum acceptable probability of rejecting a true null. So given that the null is true, and how often are we going to falsely say that it's not true? But then there's also this beta, type 2 error rate, which is the maximum acceptable probability of not rejecting a false null. So if we assume that the given null hypothesis is not true, that some other hypothesis is true, then how often do we reject that null? And there's going to be a maximum acceptable probability of failing to do so. So that's why both of these are these failure rates. This is often hard to talk about. So usually, instead of talking about type 2 error rate, we talk about 1 minus it. And that's this term statistical power. So what statistical power is, it's the minimum acceptable probability of rejecting a false null. It is just 1 minus the type 2 error rate. So a good statistical test has got high statistical power and low error rate. But the 2 trade off with each other. The lower you make your type 1 error rate, then you end up getting lower statistical power. The higher you make your error rate, that's often a way to get higher statistical power. The more samples you do, then you start unleashing the ability to keep your error rate low and increase your statistical powers. So for the same number of samples, statistical power and error rate trade off with each other. Now, in order for me to talk about the statistical power or type 2 error rate, I usually have to then define what is a sort of specified distance of like how far away from the null do I have to get for me to consider that to be significantly different from the null. So a fair coin is kind of an ideal, but maybe 45% heads to 55% heads, maybe we'll call all of that fair. And then now the question is, did I flip enough coins to be able to detect whether I'm outside of that window? And that is something that you'll see on part 2 of your homework. That's what you're going to do on part 2, where I will say, how many samples of this process do you need to detect a certain number of requests difference from a distribution? And that's what we're kind of talking about here. So the kind of what goes into these so-called power analysis here is, if I want to figure out how many samples I need, how many games to play, how many elections to run, I need to know what your desired error rate is. I need to know what your desired statistical power is. I need to know what your minimum detectable difference from the null hypothesis is. I need to know what test you're using. And then I also need to know how variable your data are. And sometimes you actually have to run a separate pilot test to estimate variability to be able to do this. And so a good statistical practice is you estimate your variability, you know all of these ahead of time, and then from there you calculate how many samples you need, and then you go out and take the rest of your data to figure out how many samples you have here. A lot of times you don't have enough time to do that, so you just start taking, you'll say, I'll take 100 samples. And the downside of that is you might find out afterwards that if you don't reject anything, if you also find out that your statistical power with that many samples is really low, then you pretty much can't do anything with your data set. So if you take a few number of samples and you reject some hypotheses, you're good. If you take a few number of samples and you fail to reject any hypotheses and your statistical power is really low, then that means that you needed to take more samples. So that's something that this is the where I'm trying to take you guys. So hopefully by the time you do the second problem in your homework, this will make a lot more sense. All right. Now, so there are alternative scopes or alternative approaches. So later on in your life, you might hear about Bayesian approaches to statistics. And these approaches actually have the ability to accept hypotheses, not just reject them. And they have the ability to use prior information, like prior games that were played outside the tournament, and so on and so forth. And they have their own problems, but it's a different set of problems, and they have a different set of advantages. And so it's outside the scope of this course, but you should know that there are these Bayesian approaches, whereas in this course, we talk about so-called frequentist approaches. So this is frequentist, kind of where everybody starts, but then the next step in your statistical career, you'll end up learning about Bayesian approaches, which are a little bit different. All right, so any questions about that? Just basic background on stats and hypothesis testing that we'll need now that we need to do parameter estimation. Okay. All right, so talked about all this stuff. So this is what we're doing today. After we've chosen a family of distributions, we've done the QQ plot and then the PP plot in that order, and we've decided on a particular family, then now we need to fit the parameters of that family. So what I mean by that is, like with binomial trials, it has a certain set of parameters that have physical meaning. So if I've decided that I want to fit a particular discrete distribution to a binomial distribution, then that binomial distribution has a parameter which is the success probability of each one of those Bernoulli trials. And so that has a real meaning. And I need to say, if these data are distributed like a binomial, what's the best binomial for these data? That means what's the P that best corresponds to these data. But they might also represent shape. And so I might say these data I think are uniform. Well, if they're uniform, then what's the range of it? I might say these data look triangular. Okay, if they're triangular, what's the range and what's the mode? If it's a normal distribution, what's the mean and standard deviation? So I figured out the shape, and now I need to figure out which of these shapes, of the family of things that all look like this, then which one of those do I pick? And that's the parameters of these distributions. So when we talk about shape parameters, sometimes we'll talk about location, scale, and rate. And so a location parameter, which is very often the mean, is a parameter that represents how you could, if you were to shift the distribution left or right, then you get another distribution that still is in the family. So as an example, an exponential distribution does not have a location parameter, because if you take that location parameter, or that exponential, and shift it away from the axis, it becomes something else. It's not an exponential anymore. But instead, we also have scale parameters, which means if you take the distribution as it is, and you take the x-axis and you stretch it or compress it, the resulting effect on the distribution gives you a distribution that's still in the family. If that's the case, then we say it's a scale parameter. And so an exponential distribution is a scale distribution that has a scale parameter, because you can stretch the axis and you just get other exponential distributions. Anything else in the other parameter is called a shape parameter. So I've got examples of that down here. If z is a standard normal and x is another random variable that I've defined by, I take the distribution for z, the standard normal distribution, and I subtract something called mu, and I divide that by something called sigma. If the resulting standard norm with this little transformation of its arguments results in a distribution that is also a normal distribution, then we refer to mu as a location parameter and sigma as a scale parameter. That's what I mean by location scale. So normal distributions have location and scale parameters. Exponentials only have a scale parameter, and that's that rate parameter, or that's, sorry, the 1 over the rate parameter. And when we talk about scale, 1 over scale is rate. So if you hear these terms, rate, scale, scale is usually associated with standard deviation, but it doesn't have to be. So, so this is how all of these kind of terms relate together. Rate is 1 over scale, or 1 over standard deviation, those sorts of ideas there. Locations typically mean. So those are the special shape parameters. Everything else is just, it just perturbs the shape in ways that are more generic. Okay, so those are our different parameters. Any questions about these, sort of the names of these parameters here? We have location, scale, and shape parameters. Okay. All right. Now, before we actually get to estimate those parameters, we have to also talk about summary statistics. And these are not parameters of distributions, but we use them to estimate parameters. So if I give you a bunch of data, I might ask you to calculate the sample mean and sample variance of those data. And so this is not estimating a parameter. This is actually saying, for the little subsample that you've selected, then what's our estimate of the mean of the whole population? And we get that by just taking you know, an arithmetic mean here. So we add up all the points, we divide by the number of points, and that gives us our arithmetic mean. So that's kind of the easy one. Now, the standard deviation, this is where it gets a little more complex because of this n-1. So this is where people usually get tripped up, because when the sort of formal definition of standard deviation kind of suggests that this denominator should be an n, but when you're doing the sample standard deviation, it's an n-1. And so, and we'll talk about more about this when we get into chi-squared, but the formula for standard deviation is basically an average of the number of deviations from the mean. So if I estimate the mean, that's so this x hat or x bar is, and I take every data point, I can see how far away it is from the mean. I can take that and square that, it's like squared error, and add up all, and then take the average of all the squared errors. Now I use n-1 here because I don't use the actual population mean, I use an estimate of the population mean. And so in other words, I don't actually have n numbers up here. I effectively have n-1 numbers in the numerator, because once I know the mean, I only really have n-1 degrees of freedom left over. So if you tell me the mean and n-1 of your samples, I can automatically figure out what the nth sample will be. So if you're using a sample mean to calculate a standard deviation, then you have to divide by n-1 because you're only actually adding up n-1 degrees of freedom in the numerator. That's the reason why that's got to be there. If you divide by n, you'll get a biased estimate of the standard deviation. So when you calculate standard deviations on your homework, you're going to need to remember to divide by n-1, not by n. So any questions about that? Hopefully that's review, that you guys have seen the unbiased estimate of standard deviation before. Questions online? All right, so I can also translate that to discrete distributions. So in a discrete distribution, like you'll see on your homework, I'll give you frequencies for outcomes. So there might be k outcomes, and each one has a certain frequency. All of those k outcomes together, they add up to the total number of samples. And so the actual outcomes, like the value of the outcomes, are the x's here. So I take whatever the x is times its frequency, add up all those together. That's how I get the mean. And then I've got effectively the same expression for sample standard deviation, but I just factored the frequencies out. So it ends up being the outcome minus the sample mean. That whole thing squared and gets scaled by the frequency. And again, by n-1, because I use an estimate of the mean and not the real mean. And then likewise, I could do that if I gave you a continuous random variable in a histogram. I can treat it like a discrete random variable where every discrete outcome is the midpoint of the histogram. And it's the exact same formulas here. All right, so any questions about that? It's a simple sort of summary statistics, sample mean, and sample variance. Okay, so if I look at, like, say, and this is very similar to the homework here, I can give you a discrete random variable like this. These are the outcomes. So this is counting up events that happen in a time period. And so for every time period I look at, there were 12 time periods that 0 things happened in, 10 time periods that 1 happened, and so on. So that's my frequency vector. That's my outcome vector. So if I want to calculate the mean of this table, I have to, and this is exactly the math you'll do on the homework, I have to scale each one of these outcomes by its frequency and then add that multiplication together. So I multiply element-wise all the way down here. All of those multiplications, I add them together. I get a number, 364, divide it by my n, which is all of the frequencies added together, 100. And that tells me that my mean is 3.64. Now, there is for the standard deviation here, I'm making use of one of these side formulas. So there is this little trick here that if I know the sample mean, I can actually simplify the standard deviation formula by just using the square of all the outcomes instead of calculating this difference. And so that's just what I've done here, where I take the square of all the outcomes multiplied by their frequencies. That gives me this number. And then I've got this little formula here divided by 99, not 100. It gives me my sample variance. And if I take the square root of that, that'll give me my sample standard deviation. So that is how I can estimate these two things from these data. Now, and any questions about any of these? Again, hopefully this is pretty review, the sample mean and sample standard deviation, the 99 kind of being the weird thing here. Okay, so now the reason I bring this up is in the Poisson, the mean of a Poisson and the variance of Poisson match in the distribution. So in theory, if I want to estimate the mean or the variance, in theory, you'd say, well, maybe I could use this one, or I could use this one, either one to estimate both. But this sample variance is much different than this sample mean. And so that just goes to show that when we talk about sample means and variances, there's a confidence interval that's hidden in there. That once we start talking about confidence intervals, then we'd see that if we put a confidence interval around the sample variation and the confidence interval around the sample mean, those confidence intervals would overlap, and the values that overlap would probably be the true values for both of those. But without worrying about that, then we have to sort of ask the question, well, if we need to pick a point to estimate this parameter for the Poisson, which one do we use? Or is it some formula that combines these two together? And so that's what we need, is a method for estimating the Poisson parameter, because we can't just use the mean, assume the sample mean is equal to Poisson's mean, because by the same logic, we could assume the sample variance is equal to Poisson's variance. In that case, these two numbers should be identical, but they're not. So which one do we choose? So that's what we need to learn how to do. So summary statistics describe data without reference to the distribution. So how do we generate general point estimates for these distributional parameters? And the approach that we're going to use, which again is to hopefully be review, is maximum likelihood. So we can take a discrete probability mass function or a continuous probability density function, and we kind of reverse how we use them. We know the data, we don't know the parameters. So we're going to take the data that is from our real system and plug it into the PDF or the PMF. And then what's left will be the parameters. Those will be free for us to choose. So we're just going to then choose parameters that will maximize either the density or the probability mass for the particular data. So as an example of that, here's an exponential distribution. I've got data that I know is exponential, or at least I want to know what the best exponential for these data are. So I know the exponential PDF up here, and I've got a bunch of data points. So like 100 data points or something like that. So in data points. So I want to say for these in data points, what's the best exponential rate that I can put in there? Well, what I can think about is I have a joint distribution of in points, where in theory, those in points could depend on each other. But I'm assuming that every sample is independent of every other sample. So the joint distribution of those in points is just the product of the individual distributions. And so fortunately, I know the PDF for the individual distributions. I can just plug that in. And that tells me that the joint distribution for any n samples of data is this thing here, which is just basically a bunch of exponential PDFs multiplied together. And if I plug in my data here, then I only have a single lambda that I need to solve for. So I can take this thing, take its partial with respect to that lambda, and I get a derivative. And if I set this thing equal to 0, then the stuff in blue here is the only thing that's going to survive that operation. So I'm effectively just setting the thing in blue equal to 0. And if I solve for lambda, then lo and behold, I find that the maximum likelihood estimate for the rate parameter in an exponential is 1 divided by the average value of the outcome. So this is an example where we get functions of those sample statistics often out as our maximum likelihood estimators. So just coincidentally, that doesn't have to turn out this way. It happens to be that the maximum likelihood mean for an exponential is the sample mean, or the maximum likelihood rate is 1 over the sample mean. All right, so any questions about that process? Fortunately, you don't have to often do the maximum likelihood process yourself. You can look them up in tables, but this is the math that underlies every maximum likelihood estimate, is you're plugging in data into a hypothetical PDF or PMF, and then you are maximizing the PMF or PDF with respect to the parameters you don't know. And then the resulting parameters that maximize that end up becoming your estimates of the right parameters. So questions about that? Does that make sense? Again, you probably did this example in 380. Okay. So like I said, you often do not have to do this on your own. You just look them up in tables. So in Banks table 9.3, they've got these ones already listed. So for Poisson, the maximum likelihood mean is the mean for an exponential. We just saw that. For a normal, the maximum likelihood mean is the sample mean. The maximum likelihood variance is the sample variance, so long as you're using that unbiased form with the n-1, similar with log normal. So these all happen to kind of make intuitive sense, but there are plenty of maximum likelihood estimators that are much more complex functions of the sample stats. So don't assume that the sample stat is a good estimate for your parameter. All right, so that's one way we pick the points for these parameters. So any questions of that? in the last couple of minutes, I want to start on goodness of fit, and then we'll finish it up next time. Okay, so after we've picked parameters, then we often want to then evaluate how good the total combination is. Did we make a kind of a good choice there, or do we have to go back to the drawing board? And that's what goodness of fits tests kind of help us with. We're going to use them in two contexts. One for input modeling, where we estimate the choice of our distribution and our parameters. So in this case, the parameters will be estimated from data. And so this is like the difference between part A and part B. So I'm putting this here because in part C of the homework on part 1C, I ask you to compare part 1A to B. This is the answer to that. So those of you who have watched the video or hanging out for here, this relates to that answer there. Is that basically when you estimate parameters from data, you're doing input modeling. But when parameters are given, you're doing output validation. So if I say that the simulation needs to produce an exponential or a Poisson with a given mean, I'm saying that because in the real world, it's an exponential with this mean. And if the sim's working correctly, it'll produce the same thing. That's output validation. But if instead I only know is there is a exponentially distributed interarrival times, and I want to know what parameter to put into ARENA, then I'm estimating a parameter, and that's input modeling. So when you estimate parameters, you're doing modeling. When your parameters are given, you're doing validation. And so that will hopefully make sense as you look at part 1 of this homework. So, and this is just a reminder of our very little data means that if you have a large p-value, you can't trust it. Very much data means a small p-value, you can't trust it. So danger of just looking at p-values. All right, so the big goodness of fit tests that we're going to lean on are the ones you've already seen before. Like I said, I'll probably start roughly around here next time. But just to give you a preview of where we're going with it, is we've already looked at the chi-squared test for the uniform distribution, and now we're going to revisit the chi-squared test for any distribution. And then we're going to find out the chi-squared test has low statistical power. And so what that means is that when you have a low number of samples, you've got to use another test. And now we're going to revisit the KS test, which has high statistical power. And so we'll show you how to use the KS test for any distribution, not just uniform. Now, because the KS test has high statistical power, you don't want to use it when you have a whole lot of data, because the KS test will always reject any hypothetical distribution, because it has so much power that it needs very few data points in order to make that rejection. So that's kind of where we're going to go here. So that's why even though the KS test works for small numbers of samples, most of the time you're going to have enough data that will actually be better using chi-squared. And so that's kind of what we'll start talking about next time. But I'm going to hold off on that for now and just give you guys a break. And so we'll end here with an attendance exercise, and I'm happy to take any remaining questions after here. So let me just get the chat back in Zoom. And so the question I have here is, when should a very low p-value not be trusted? Under what conditions, what special condition, I'm looking for one in particular, if someone gives you a very, very, very low p-value and says that hypothesis is bunk, you should not, that is rejected, then under what conditions is maybe that a little bit extreme and you shouldn't trust that low p-value? And that's all I've got for you. So otherwise, I guess I will see you on Tuesday, and have a good weekend. Are those online? That's all I've got as well. If you have any questions, I'm happy to take them. Otherwise, have a nice weekend. All right, people starting to pop off, so I'll go ahead and end the meeting.